This is assignment 5 by Caleb, Jack, and Travis. Part 1 for project 5 was to show what the phase diagram for our metal A and metal B were when they form an alloy, where our metals were copper and palladium. The first graph on the left shows the phase diagram for copper and tin, and the graph on the right shows the phase diagram for palladium and tin.
Next, we'll be talking about the lever rule in allotropy. So the lever rule is a mathematical technique used to determine amounts of different phases present in a system at equilibrium. The system is based on math because the total mass of the system must remain constant. So for example, when a solid and a liquid phase coexist at equilibrium in a binary phase diagram, the lever rule can determine the percentage of each phase present. And lastly, the lever rule is important because it allows the user to predict and control the phases. So you can see on the screen that the lever rule equation is F equals C minus C1 over C2 minus C1, where F is the fraction of one phase, C is the overall composition of the system, and C1 and C2 are the compositions of the two phases. So moving on to allotropy. So when elemental solids have more than one crystal structure, that's what allotropy is. The prevailing crystal structure is based on the temperature and the external pressure, and physical properties like density will change with these crystal structure changes.
Eutectic. What does it mean? The term eutectic is when the metal mixture cools down from a liquid phase into a composition of two solids. To the left of the blue line represents hypoeutectic, where it cools down from a liquid into a solid with pockets of alpha solid, and then a laminated mixture of both metals surrounding each of the pockets. To the right of the blue line represents hypereutectic, similarly to hypoeutectic, with the pockets of material, except the pockets are beta instead of alpha solid, with the same laminated mixture around each of the pockets. Eutectoid. What does it mean? Eutectoid is when a single solid phase transforms into two different solid phases at the same time at a specific temperature and composition. Gamma, represented by light blue, turns into iron carbide, and alpha, represented by the orange and blue. To the left of the dashed line represents hypoeutectic portion of the phase diagram. Here, we can see that there is more of the alpha solid, which is represented with the orange portions of the microstructure drawing. And then on the flip side, to the right of the eutectoid line is hypereutectoid. Similarly, this has an uneven distribution of material. Here it has more iron carbon. This is represented with the large veins of blue in the microstructure illustration at the grain boundaries.
Peritectic is when one liquid and solid phase create a second solid phase. The way the crystals are formed is shown on the drawing to the left, where a solid and liquid create a second single solid with grain boundaries. The point where the crystal is formed on the phase diagram, it would be at point E with a straight vertical line. Hypoperitectic and hypereutectic are similar to peritectic, where a liquid and solid phase create a second solid phase, with the only difference being the composition.